Thanks, Nima. I have not actually spent a lot of time preparing the lecture, but I have spent a lot of time preparing the notes. So I'm just going to read from the notes. And I urge you to look at them on the website, and it's a work in progress, so update it from time to time, at least over the next few days. Okay, so this is a course, as you can see, about BPS states and wall crossing in four-dimensional n equals 2 theories. And BPS, it was realized in the course of certain breakthroughs in the mid-1990s that an important concept was the concept of BPS states. These, as I will say in more detail, are rigid representations of supersymmetry, and that rigidity allows you to say things about non-perturbative theories. This was one of the main insights. And therefore, you can take results from weak coupling and learn about non-trivial things at strong coupling. Well, it turns out that you have to be careful about that, because while the BPS spectrum is constant, it can still jump. And this is the wall crossing phenomenon we'll be talking about. This was, I think, first realized in the context of two-dimensional theories with 2,2 supersymmetry in a paper of Cicciotti, Fenley, Intrigligator, and Vafa. And then later on, Cicciotti and Vafa gave some quantitative formulas for how the BPS states changed in these two-dimensional theories. And then in the breakthrough of Zyberg and Witten, the wall-crossing phenomenon, at least qualitatively, was very important to verifying the consistency of the picture that they came up with. In the last 4 years, we've learned a lot of new things about the quantitative ways in which BPS states, the BPS spectrum changes. Now, that's motivation enough for understanding this wall-crossing phenomenon, because it's important to understand things about non-perturbative theories. But in fact, it's turned out that the study of BPS states has led to a very, very rich field of mathematical physics. And in the notes, I give a list of all of the interesting, well, not all, but some of the interesting topics that have connections to or have emerged from the study of BPS states, including the Strominger-Vafa program for accounting for the entropy of black holes, the Bekenstein-Hawking entropy of black holes by counting microstates, going all the way up to the latest developments relating four-dimensional theories to two-dimensional integrable systems, which has been an important theme in the last year or two. So I'm not going to write all that out. We have quite a lot of material to cover today. So let's just jump right in to the technical details. Oh yes, the other thing is, normally I would give an overview of a mini course at this point, but again, in the notes, there's an outline at the beginning of the notes, and that's a sufficient overview for you. So let's jump into the details. And the first thing we want to talk about is the n equals 2 superalgebra. Now, I know John Bagger covered some of this, but let me just set up some of the notation. So it's a superalgebra. I'll denote it by S, so it has an even piece and an odd piece. And the even subalgebra is the Poincaré algebra, and then an R-symmetry algebra, which we'll split up as SU2 and U1, and then a piece for the so-called central term. And then S1 is a representation of S0. That's part of what it means to be a superalgebra. And the representation is 2, 1 of Poincaré, the 2 of SU2R, charge +1 under the R symmetry. C is central, so there's no charge. Direct sum 1, 2 to -1, and then there's a reality condition on this. We say what the reality condition is. Usually we choose a basis for the odd superalgebra. We'll denote it as Q alpha A. The alpha, as in Bess and Bagger, is a Weil-Spinner index. The capital A goes from 1 to 2. That's an R symmetry index. And the reality condition is that this is equal to Q bar alpha dot A. And then we have the anti-commutators of the odd with the odd into the even. And so those are Q alpha A, Q bar beta dot B is equal to 2 sigma M alpha beta dot P sub M delta AB. P sub M are the Hermitian momentum, energy momentum vector. We also have Q alpha A, Q beta B is 2 epsilon alpha beta epsilon AB Z bar. Z is the central term, the central extension. And then Q bar we can get, and then we can take the complex conjugate of this equation. Are there any questions about notation? I'm mostly following Bagger and Wes. Are there any questions about notation or what I've said so far? All clear? All right. Now, one important remark about this SU2R symmetry, it's there in field theory, but generically it is not there in supergravity, in string compactifications, on compact Calabi-Yau manifolds, and we'll see later on why that's actually an important thing to say. Okay, so the next thing we want to do is talk about particle representations of these superalgebras. I guess I can and we're going to consider the particle representations using the method of Wigner. So we're going to consider massive particles, and we can bring massive particles to rest, and that means we use the method of induction, where we bring the particle to rest, we look at the symmetry algebra of that, and then we induce the representation by boosting from that. So a particle representation is in part characterized by the mass squared. The m will be bigger than 0 for us. And we can bring a particle to rest like that, where there's a factor of m here. And then the little superalgebra, I'll call it S0L plus S1. Oh, I'm using calligraphic S for this. The little superalgebra has an even part, which is SO3 rotations around this particle at rest. This massive particle at rest is sitting at a point, so we can rotate around. The R symmetry is coming along for the ride. Okay, and the odd symmetries are still there. So now what we want to do is we want to find finite dimensional representations of finite dimensional unitary representations of this superalgebra. Okay? And what we should do then is we should look at the odd part of the superalgebra, and that is basically a Clifford algebra. As we'll see, it has a non-degenerate form, and a Clifford algebra with a non-degenerate form has a unique irreducible representation. So let's assume that z is not 0, because that's going to be the case that we're mostly interested in. And John has explained what happens when z equals 0. So let's also define a phase alpha by z equals e to the I alpha, absolute value of z. And then, as I mentioned, we've got this massive particle at rest. And so it suggests the following automorphism of the algebra. If the massive particle is at x equals 0, then it's invariant under parity. X goes to minus x. So I'm going to take an involution of this algebra, where I take this parity transformation and I also do a U1R symmetry rotation. And you'll see why this is useful now and also in lecture 3. And I'm going to split up the odd part of the superalgebra into the even parts and the odd parts under that involution, where the even parts are generated by what I'll call the R supersymmetries. And the odd parts are generated by the T supersymmetries, where I simply put a minus sign there. This psi is a phase, and mostly we'll be working with psi squared, which is the phase I'll call zeta to the minus 1. Now I put the, I didn't just write it as q plus zeta q bar because I want to have some nice hermiticity properties. For example, R11 dagger is minus R22, etc. Now, having made this change of variables, we can now recompute the supersymmetry algebra, and we'll see that we've partially diagonalized the quadratic form. A straightforward calculation, which I leave to you, shows that it looks like this. And T alpha A, T beta B is 4 times minus m plus the real part of z over zeta, epsilon, epsilon. Okay, now we can already learn something interesting. If we take these relations and this kind of hermiticity relation, then we can calculate R11 plus R11 dagger squared. Well, the R11 dagger is like an R22. And so this is equal to 4 times m plus the real part of z over zeta. Okay, now, this is the square of a Hermitian operator. And the square of a Hermitian operator is positive semi-definite. And so we see that in unitary representations, we have the mass is greater than or equal to minus the real part of z over zeta. That's called the BPS bound. Okay, and it holds for any zeta. Now, we can get the strongest bound by taking zeta equals minus e to the I alpha. And then we get m is greater than or equal to the absolute value of z. Now, the reason I did it this way is that in lecture 3, we're going to look at these same supersymmetries, but we're not going to have the freedom to vary zeta. The zeta is going to be part of the input data, and then we'll have this BPS bound coming back. But for the moment, we can choose zeta to be anything we like. And so we choose it to be this, and then we get this BPS bound. So this is the BPS bound. Okay? Now, when we make that choice of zeta, we get an extra nice thing, which is that the r's anti-commute with the t's. Okay, and so we very nearly diagonalized this Clifford algebra. And so now we can start to talk about representations. Okay, so when the other thing is that when we've diagonalized, when we've chosen this phase, then this simplifies in an interesting way. This is m minus the absolute value of z, pull out an overall minus sign, m plus the absolute value of z. So that means that we should first consider two cases. The first case is the case of long representations. And that's when m is greater than the absolute value of z. Now, when m is greater than the absolute value of z, by positive rescalings, I can define r hat equals epsilon epsilon. Let me suppress the indices. They should be obvious. Equals epsilon epsilon. So I can make some positive rescaling of my R supersymmetries and my T supersymmetries. So I have something like that. And the R's anti-commute with the T's. So now let's try and just represent the R hat Clifford algebra. Because the representation for the T's will be identical. And so let's write out the R hat Clifford algebra a little more. So it's R hat 1, 1 squared equals R hat 2, 2 squared equals 0. R hat 1, 1, R hat 2, 2 is equal to minus 1. And R hat 1, 2 squared equals R hat 2, 1 squared equals 0, and R hat 1, 2, R hat 2, 1 is equal to plus 1. Okay, so you see here we just have creation and annihilation operators for free fermions. So it would be natural to choose one of these to be the creation operator and the other to be the annihilation operator, and then take a tensor product. Now, an important point here is that this Clifford algebra is preserved by this little superalgebra here, by the SO3 and the SU2 transformation. So the irreducible representation that I write of this Clifford algebra is going to be also a representation of SO3 plus SU2R. So I could choose to look at some state, take the highest spin representation under SO3. R sub 1 has spin up, R sub 2 has spin down. So then, if I choose that state, R1A on that state omega is 0. Okay, so now I know which of these should be my annihilation operators. And then I generate a whole representation by acting with R2s. So I have R21 on omega, R22 on omega, and R21, R22 on omega. And so then we have supersymmetries acting like this. Okay, and now as a representation of SO3, we should make this a spin a half, spin minus a half. So these two form a doublet under SO3. And then this should be spin 0. And then this is a doublet under SU2R. So SU2R acts this way, and SO3 acts this way. Okay? And this basic representation now, what have I represented? I've represented S naught, what do I call it? S naught sub L, the even part of the little supergroup, S1 plus. I've represented the R supersymmetries and the little supergroup, the little superalgebra. the even part of the little superalgebra, S naught L. We have a four-dimensional representation of the R supersymmetries, and then we have a representation of S naught L, which is 0, 1/2, direct sum, 1/2, 0, as a representation of SO3 plus SU2R. So I'll call this basic representation the half hypermultiplet and denote it by rho sub HH. Now still just trying to represent S naught, the little part of the superalgebra, and the R supersymmetries, we could ask what is the most general representation? So the most general rep of S naught L direct sum S1 plus is of the form rho half hypermultiplet tensor H, where H is any rep of S naught L. Okay? That's something you can find in Wesson-Bagger. Okay. Well, now having done all that work for the R supersymmetries, you see the T algebra is just the same up to some overall rescaling. It's again covariant with respect to SO3 plus SU2R. So the story is exactly the same. So the R's and the T's anti-commute. So the most general long rep is therefore rho half hypermultiplet tensor rho half hypermultiplet tensor H for some H, where this is the four-dimensional irreducible representation of the R supersymmetries, and this is the four-dimensional representation of the T supersymmetries. Okay, and so then this is the full representation of the little superalgebra from which you can induce the full particle representation. Are there any questions about that? That's the most general, long representation of supersymmetry. If I want it to be irreducible, I take this H to be an irreducible representation. Any questions?
Can we not have two different H's for the two different?
Pardon?
Can we not have two different H's for one row and the other row?
No, that's my assertion. Of course, you see the tensor product, you see the Q's act here. The SO3 and the SU2 act in the way that you should act with the tensor product. And if I had an H from the R supersymmetries tensored with an H from the T supersymmetries, I think that's your question, then of course I could take that H and I could decompose it, or I don't even need to. All I said is that this is some representation of this Lie algebra. Well, okay, that's closed under tensor product. So I'm not saying that this H is necessarily the same as this H. I'm saying the most general representation is of this form. All right. Yeah, I should give an example. The smallest long representation is, of course, taking this to be the trivial one-dimensional representation. So that would be rho half hypermultiplet tensor rho half hypermultiplet. And if we work it out as an SO3 plus SU2 representation using this formula here, then you see that's 2, 0, 0, plus 0, 1. Those are scalar fields, plus 2, 1 half, 1 half. Well, scalar particles. These are fermionic particles plus 1, 0, and that's a vector particle. Okay. Now let's talk about short representations, also known as BPS representations. Well, what happens here is we get a short representation when we saturate the BPS bound. And you see something significant happens up here. When we saturate the BPS bound, the R's are no longer forming a Clifford algebra. They form a Grassmann algebra. So I can't go to the R hats here. So the R's in a unitary representation must be represented as 0. And these are called preserved supersymmetries. Okay, and the most general representation that we get, well, we still have the T supersymmetries. So the most general representation we get is a single copy of rho half hypermultiplet times H. Or again, H is some arbitrary representation of SO3 plus SU2R. And two examples which will be important for us is H is the trivial representation, so that's the half hypermultiplet itself. And the other example we should take is H equals 1/2 0, and that's the vector multiplet representation, which is 0, 0, 0, 0, direct sum, 1/2, 1/2, direct sum, 1, 0. So a scalar fermion and a vector particle. Okay, so that concludes particle representations. Now we also need field representations, and again, John talked about that, so let me be very brief here. So the field representations that we're going to need are, first and foremost, the vector multiplet. So let's let G be a compact Lie group, Lie algebra, the Lie algebra of a compact Lie group. And then what we have is we have a scalar field, phi. We have fermions, psi alpha A, in the 2, 1 tensor 2 of the Lorentz group and the R symmetry. They're Hermitian conjugates and a gauge field, AM, all valued in the Lie algebra, in the adjoint representation. Now, one thing that could be a little confusing here is I've been talking exclusively about massive representations. Of course, this is for the massless particles. And John talked about the massless representation, so I'm going to leave it at that. Then we also have hypermultiplet field representations, and supergravity has a supergravity multiplet. And we're not going to need those in detail. In lecture 2, I will talk about solutions of n equals 2 supergravity, and then I'll tell you what fields I need from that multiplet. Okay, so let's just leave it at that for the vector multiplet representations. But in the notes, I write out in detail the supersymmetry transformations of these fields. I'm not going to write all that on the board. It would take a lot of time. We'll use a little bit of those supersymmetry transformations later on in this lecture. Okay, so the next thing I want to talk about is the fact that we're dealing with families of theories. Okay, so one way we could get families of theories is by just choosing by varying the coupling constants in the Lagrangian. But the Lagrangians of n equals 2 theories are rather restricted. And the real important source of families of theories is that there are families of quantum vacua. And the parameter space of these quantum vacua are called the moduli space of vacua. And what we'll find is that they form a manifold. We're going to be technically restricting attention to a component of the moduli space called the Coulomb branch, where the gauge symmetry is broken down to an abelian gauge symmetry. And we'll denote it by B, and a generic point in the Coulomb branch will be denoted by little u. Now, one way to think of these is in a path integral, you can think of these as boundary conditions at spatial infinity for the vector multiplet scalars. So imagine you're doing a path integral in one of these n equals 2 theories. So you have a path integral over these scalar fields, these fermions, these gauge fields. You need to specify boundary conditions on these path integrals. Okay? And these Coulomb branch parameters can be thought of as the boundary conditions of the vector multiplet scalars. Let me clarify that perhaps with an example. So let's take pure SUN n equals 2 theory. And then what is the classical potential energy? The classical potential energy is the integral of d3x. Can everybody see this? It's okay? Hello? Awake? Yeah? Okay. The classical potential energy is the integral d3x, the integral of trace of e squared plus b squared, okay, plus the trace of the spatial derivatives of the vector multiplet scalar field squared plus trace of phi dagger phi squared. Okay, so what do you see? If you want to minimize the energy, from here you should take a flat gauge field. Now on R3 times time, which is what we're taking, a flat gauge field is gauge equivalent to no gauge field at all, zero gauge field. And then we want phi to be spatially constant. Okay, and then we want to minimize this, which means phi commutes with its Hermitian adjoint, which is to say that phi is a normal matrix. Phi is a complex matrix. Yeah, I guess I should have said, I lied a little bit. When I said these are all valued in G, I definitely lied. The gauge field is valued in G. It's a one-form valued in G, but this is valued in the complexification of G. Phi is a complex scalar field. And anyway, so minimizing the energy means that phi dagger phi is 0, which commutator is 0, which means that phi is a normal matrix, which means that it's unitarily diagonalizable. Okay, well, we have to give it some value. And so the parameters on the Coulomb branch then would be, for example, u sub I, which is the trace of phi of x to the i'th power, where for the independent ones, I should go from 2 up to n. Why didn't I choose I equals 1? Pardon? Why not take I equals 1 in that list there? Thank you. Okay, just checking that people are awake. Okay, so okay, so okay, so in this case, at least classically, our Coulomb branch would be a copy of C to the n minus 1. Now, I did a classical analysis, and the nice thing about n equals 2 supersymmetry is that it continues to be true that there's a manifold of quantum vacua. In other words, these vacua are not lifted by quantum effects. Now, another thing is that this B, as you can see from the example, is a complex manifold. Okay, it's a complex manifold. And the other important thing that we're going to see is that, well, you see, we now have these families of theories parametrized by points U on B. So we have families of families of particle representations. H sub u, where H is the set of one particle representations in the Hilbert space of the theory. So this is a theory with massive particles. A massive particle to us means a unitary, irreducible representation of the n equals 2 superalgebra. I've just shown you how to get those. There might be many particles, so we'll take the direct sum of those one particle representations. So we get some Hilbert space. Now, all separable Hilbert spaces are isomorphic as Hilbert spaces. However, that's irrelevant to physics. What's relevant to physics is how they're Hilbert spaces as representations of operator algebras, or in this case, as representations of n equals 2 supersymmetry. So if we look at the way the central charges are represented on these one-particle Hilbert spaces, they're going to be functions of U. And a very important aspect of that is that the z of U are going to be holomorphic functions. Now, in the mid-1990s, it was realized by Professor Zyberg and others that if you apply holomorphy skillfully with physical insight, then you can get non-perturbative and non-trivial information about the supersymmetric gauge theories. And this is an important example of that, as indeed shown by Zyberg and Witten. So they showed that these central charge functions can be determined exactly, and the holomorphy is a key to that. And I'll indicate later what their solution was for these central charge functions. Okay, so we have this family of one-particle Hilbert spaces. And I just said that the z of u were something that can be determined exactly. And so that motivates a key definition. The space of BPS states is the subspace of the one-particle Hilbert space, which is the set of states which satisfy the BPS bound. Okay, now an important point here is that just knowing the central charge function, which we know from Zyberg and Witten, does not determine the BPS spectrum of the theory. Because just because you know the central charge function doesn't mean that actually a representation of that kind exists. So we still have the problem of find a method to determine the BPS spectrum. And, well, I've got a room full of students, so I should say that this is an unsolved problem. There's no algorithm. If I give you an n equals 2 supersymmetric theory, you can't go look up a paper somewhere, turn out an algorithm, and churn out the BPS spectrum. We know the BPS spectrum by some ad hoc arguments in some classes of theories. So I think Davide Gaiato will be talking about so-called A1 theories in class S. He'll explain what that means. That includes the SU2 theories with NF equals 0, 1, 2, 3, 4. And for these, there's actually an algorithm for calculating the BPS spectrum. I believe that no example of the BPS spectrum for type 2A on a compact Calabi-Yau is known. Perhaps the FHSV model, but I don't think that's been done carefully. So that's an open problem. And the BPS spectrum is something of interest because of these two properties. That Z is holomorphic can be determined exactly, and because of the BPS bound, we then know the exact mass spectrum, at least for those particles. So that's what I meant by the rigidity and the solvability of the BPS spectrum. Okay. Now I want to go back and talk a little more about this family of theories. And in particular, let's look at this example here again. And as I said, phi is a normal matrix. So phi can be unitarily diagonalized to A1 through AN, okay, with the sum of the AIs as 0. And this spontaneously breaks the gauge symmetry from SUN to U1 to the n minus 1. Okay, that's what happens on the Coulomb branch. We now recognize that the UIs here are just symmetric functions made out of the AIs. Those are the gauge invariant quantities. You see, when you break the symmetry like this, you still have unbroken the Weil group symmetry, which permutes these guys along the diagonal, and therefore the gauge invariant quantities are the symmetric functions of the AIs. Yes, sir?
So the phase that you picked initially, could that vary on the modulus phase?
Yes, the way I have set that up, that was purely an algebraic manipulation, and I had some zeta. And for a particular particle that I'm interested in, I chose zeta to be e to the minus I alpha. But your question is an excellent one. If I now fix my attention on some particle, it's going to have some z if it's a BPS particle. And that z is going to be a function of u. And therefore, its phase is going to be a function of u. Absolutely correct. OK. So the thing I want to stress here is that on this Coulomb branch, our gauge symmetry is broken down to an abelian gauge symmetry. And now I see there's a mistake in the notes, a minor mistake. I'm going to say my abelian gauge symmetry is of rank R. That's what I'm doing throughout the notes. And so this n minus 1 here is R. And so everywhere in the notes when I talk about abelian gauge symmetry, it's rank R. And so I should have said SU R plus 1 theory. Okay. Yes?
Generically, gauge group breaks U1, in special cases.
Thank you very much. Yes, in special cases. Go on.
In special cases,
You mean special cases, for example, when all the AIs are 0.
and A1 equals S2 equals.
Or something like that. Yes. And in those special cases, I expect that you're going to tell me that there's an unbroken non-abelian gauge symmetry. Is that right? Yeah. So indeed, that's a very important remark, which is in the notes, but which I forgot to say. And that is that, yes, it looks from my discussion like when we have special cases where some subsets of the AIs are equal, then it looks like we have an unbroken non-abelian gauge symmetry. And that is true in the classical theory. Now, I said I motivated this by pointing out that there was this manifold of classical vacua. And then I blithely said, well, okay, with n equals 2 supersymmetry, that manifold of classical vacua is not modified, and we still have a manifold of quantum vacua. That's true. However, one of the key results and insights of Seiberg and Witten is that while the manifold of quantum vacua is not lifted, the physical excitations above that vacuum is modified by quantum effects in a very strong way. And so it's true that classically, when the AIs are all 0, we're going to have a non-abelian enhanced gauge symmetry of SUN. What Seiberg and Witten showed is, no, that's not what happens quantum mechanically. And in fact, the picture quantum mechanically is very different. We still have this manifold of vacua. There are going to be some singular points where something special happens, or singular codimension 1 and higher codimension varieties. But everywhere here we have abelian gauge symmetry, and something different happens at the singular points. So for example, the example that I was planning to discuss in more detail later, in fact, I will discuss it in more detail later, so hold off and I'll come back to that point.
Does this argument also apply when the A's are not equal, when the A's are non-zero but equal?
Well, that's an example when the A's are non-zero but equal. We'll still have some unbroken gauge symmetry, quite correct. Well, okay, so you see, when the A's are all equal, remember that since we're dealing with SUN, as I was stressing before in my question to the audience, we have that. So if the A's are all equal, they're 0. Okay? So the A's all equal corresponds to a U1 factor, but I've dropped that. But more to the point, if some subset of the A's are equal, then we'll have an unbroken gauge, non-abelian gauge symmetry classically. What I'm saying is that Seiberg and Witten showed that that's not what happens quantum mechanically. It's a fundamental point. So quantum mechanical effects do not lift the manifold of vacua, but they strongly affect the excitations, how you describe the excitations around that vacuum. Okay. Now we've got this abelian gauge symmetry. And therefore, we can have dyons, which are particles with electric and magnetic charge. Now, when I say electric and magnetic charge, we've broken this down to U1 to the R. So there are many photons. There are different photons, okay? And we are talking about electric and magnetic charge with respect to all those photons at the same time. So I take it that generalization is pretty clear. And then in the problems, in the notes, I give you the important problem where you take two dyons of, let's say, charge E1, M1 and E2, M2. And I ask you to calculate the angular momentum around the midpoint of the electromagnetic field. Now you see, the electric field from this guy is going to come out like this. The magnetic field from this guy is going to come out like that. The cross product, which gives you the momentum of the field, is going to come out of the board like that. And then if you think about it, it's symmetric, so it's going to go back into the board over here, so it's going around. So there's angular momentum in this system. And the angular momentum is J equals E1 M2 minus E2 M1 times R hat, maybe with a, I don't remember the factors of C and so on. And I think there might be a half here. When I set H bar and C equal to 1, there'll be a half. Okay, so what we learn is Dirac quantization on electric and magnetic charges, and the correct generalization of that is the following. Dirac says that the electric and the magnetic charges are vectors gamma in a lattice, capital gamma, which is symplectic. That means that there's an antisymmetric product from gamma times gamma to z. And moreover, that antisymmetric form is non-degenerate. Now, you could include, and in fact, it is good to include flavor charges. Now, here I'm just talking about gauge charges. If you include flavor charges in your description of the charges, you will still have an antisymmetric integral valued form, but it won't be quite non-degenerate. It'll be what's called a Poisson lattice. That's a detail I don't want to get into. So in these lectures, we're simply going to assume we have a symplectic lattice of charges. Now, when you have a symplectic lattice of charges, you have a vector space, gamma tensor R, which is a symplectic vector space. If you don't know what the tensor means, think this way. Choose a basis for your lattice, so it's just a tuple of integers. Now just let those integers be real numbers, and you have a vector space. Okay? And you won't go wrong. Okay, now why am I introducing this symplectic vector space? Because it turns out that in the Seiberg-Witten solution, the low energy abelian gauge theory is a self-dual abelian gauge theory. Now, there's a long and technical subject of self-dual gauge fields, which this is not the place to get into. But I'm going to give you a flavor of that subject, which is relevant to our current considerations. So the basic idea is that when we want to describe these low-energy abelian gauge fields, well, they're going to have some field strength. And a field strength is going to be a two-form on space-time, which I denote this way. A two-form on space-time, but it's valued in this vector space V. Now, I should have said that since we have a rank R gauge group, we have a rank R abelian gauge group, the rank of gamma is, anybody? 2R. Because for one abelian gauge field, there's an electric and a magnetic charge. So for R gauge fields, there are R electric and R magnetic charges, and it's 2R. Okay? So that means that this vector space V has rank 2R. So you should be saying at this point, wait a minute, that's too many gauge fields. And I'll ask you to just be patient. Okay, so in order to define this self-dual theory, we need some data. And the data we need is a positive, compatible, complex structure on V. So what does all that mean? Well, first off, a complex structure is a linear transformation. V is a vector space over the real numbers. So it's a real linear transformation from V to V such that I squared equals minus 1. That's what a complex structure is. Okay? It's compatible means that the symplectic inner product of I of V with I of V prime is V with V prime. For all vectors V and V prime in my vector space. And positive means the following. So if you use this compatibility, you see that G of VV prime, which by definition is the symplectic inner product of V with I of V prime, is symmetric. G of V prime V. So the angular brackets are anti-symmetric, but G is symmetric. And we will assume that this symmetric form is positive. And later on, you'll see why we need to assume that. Okay, so that's the data I need to formulate this self-dual abelian gauge theory. And I told you where F lives. And now let's formulate it. So there are only two things I have to say. The first is the Hodge star is minus 1 on two forms in Lorentzian signature. So we're assuming M4 has Lorentzian signature, so the Hodge star squares to minus 1. Therefore, if I define the operator little s to be Hodge star tensor I, the complex structure, then s squared is plus 1, because complex structure squares to minus 1. And so the first thing we say is that the gauge field is self-dual. So that's cutting down. You see, I said you could have objected that I had 2 times as many gauge fields as I wanted physically, but now I've cut it down by this projection. Okay, by the self-dual projection. Now, of course, half the world will choose the orientation that you like for R4, but the other half of the world is going to choose the opposite orientation, right? And so it would be wise, and we will do it, to put in an epsilon, which is plus or minus 1. So we have epsilon plus 1 is self-dual, and epsilon minus 1 is anti-self-dual. Okay, then we need to specify some dynamics, and we do so simply by saying F is flat. Okay, and now we have actually specified the dynamics of an abelian, self-dual abelian gauge theory. Now, it might not look to you like there's a whole lot of physics here. To extract some physics, what we need to do is we need to choose a duality frame. Okay? What a duality frame is a choice of Darboux basis for our symplectic lattice gamma. And what that means is that we choose some vectors, and I have alpha lower I and beta upper I, So these are basis vectors in gamma. Gamma is an integral lattice, so that means that vectors in gamma are integer combinations of alpha I and beta I. And the Darboux-ness means that alpha I, alpha j, and beta I, beta j is 0, and alpha I, beta j is delta I j. Okay? So that's what a duality frame is. In mathematics, it's usually called a maximal Lagrangian decomposition. Because the sublattice spanned by the alphas is a Lagrangian sublattice. Every vector in that sublattice has inner product 0 with itself, and same for the betas, and the two things span the whole lattice. Okay, now I said that we have this data, this positive compatible complex structure on V. And so now let's use it. So if you have a vector space V with a complex structure and you complexify it, then you can diagonalize the complex structure. And so you get the 0, 1 part and the 1, 0 part. And the complex and I extends to a complex linear map on V tensor C. And I is equal to minus little I on 0, 1 and plus little I on 1, 0. So given a Darboux basis, we can now choose a basis, f sub capital I for V0, 1, and it will be of the form alpha lower I plus tau ij beta upper j, where this I here is going from 1 to R. And the reason I'm doing this is I'm showing you that if you choose a duality frame, then this data of a complex structure is summarized in this matrix right here, which is called the period matrix. And it's a very important quantity. Indeed, the compatibility tells me that the period matrix is symmetric. And it will be very convenient to write it in terms of its real and imaginary parts, like so. That's what x and y are. And then the positivity says that this symmetric real matrix Yij is positive definite. Okay, now, you can now, since y is invertible, you can now take this equation and the obvious equation for its complex conjugate, invert that to write alpha and beta as functions, as linear combinations of f and f bar, calculate what I does on the alphas and what I does on the betas. And it's some exercise in linear algebra, which I leave in the notes. And this will be useful for now extracting, as I said, the physics once we choose a duality frame. So let's do that. So we have this f. Okay, it's valued in this symplectic vector space. So it can be written as a linear combination of alphas and betas, where the fi and the gi are each two forms on space-time. Right? So here are twice as many two forms on space-time as we wanted physically. But now we impose the self-duality condition. Okay? The self-duality condition involves the Hodge star. We just leave that as Hodge star. And the capital I, we know how the capital I acts. And so what you find is that A is equivalent to g sub j equals minus epsilon y sub jk star fk minus x sub jk fk. Okay, and then B tells me that first of all, d of fi is 0, and d of gj, well, that's also 0, right? because curly f was flat. But G is also equal to this mess. So it's equal to minus epsilon d of yjk star fk plus epsilon xjk f upper k, and that's equal to 0. Okay, well now you can recognize some dynamics. These are the Bianchi identities. And these are the other half of Maxwell's equations. You see, just forget about the x's and y's. Those are just some matrices, maybe some space-time dependent matrices. But I hope you all know that Maxwell's equations are df equals 0 and d star f equals 0, at least in vacuum. And there you can get some dynamics. So Maxwell wrote those equations down in 1864 and calculated the speed of light. Good day for Maxwell. Okay? So you get some dynamics out of this. Now, another interesting point is that having chosen the duality frame like this, we also get a Lagrangian. So it's a curious thing that if you formulate the self-dual theory in this duality invariant way, as it's called, then there's no covariant Lagrangian description that derives those equations. Try it yourself. You'll be famous if you succeed. Try and write down a covariant local Lagrangian whose equations of motion gives A and B. You can't do it. But if you choose a duality frame, then it's a piece of cake. Because you see, the Bianchi identity tells me that Fi is dAi. So there's a gauge potential here. And then we can write down the action principle y sub jk fj star fk plus epsilon xjk fj fk. And you can check that now those equations are those are the Euler-Lagrange equations for this action principle. Let me make a few remarks. Now we can finally see why we impose this funny positivity condition. We impose the positivity condition because of that term there, the kinetic term, in the Lagrangian. And so for a physically reasonable theory, we want this yjk to be positive definite. Also, imagine that we could diagonalize yjk. Then it might look something like this. 1 over ej squared delta jk. So we recognize that this y here is just the coupling constants of the theory. These are just the electromagnetic coupling constants of the theory. That's what y is. X is what's called an axion coupling constant. And the period matrix is therefore to be thought of as a complexified coupling constant. Also note that the parity odd term in the Lagrangian indeed comes with an epsilon, as it should, so I didn't make a mistake there. Now, of course, there are many duality frames. There's no unique duality frame. I made a choice of Darboux basis. Another choice, alpha I tilde and beta I tilde, would be related to this choice, alpha I and beta I, by some matrix M. And that matrix, as you show in an exercise, is in SP2RZ in the symplectic group with integral coefficients. And then you can go on and work out, in terms of M, all the transformation laws of the alphas, the Fs, the taus, the field strengths, and so on. It's straightforward linear algebra. If you're actually thinking of working in this topic, then you've got to do it. You've got to know this extremely well. And so there's an exercise in the notes that guides you through that. How am I doing for time? Terribly. Okay, so got about halfway through lecture 1. We'll take it from there tomorrow.